Okay, so before we get going on the new stuff, okay, the new problems with the pH and the acids, base, and so on, I just want to review a little bit of the problems we did last. Again, remember that the H plus and or the H3O plus, they're the same thing because hydronium, which is H3O, is just water plus a hydrogen. So you can write it either way, it doesn't matter. But anyway, if I've got the concentration and I want to know the pH, again, it's hard to tell from this. Okay, but if we switch it to a pH, which is a number from 0 to 14, it's easier for us to understand. So if I take this number, if I take the log of 2.5 times 10 to the negative ninth, I get 8.6. You actually get negative 8.6 because, but remember, we lose the negative. I think I put that a bunch of times in your worksheet, so I'm hoping you get it now. But anyway, 8.6, that tells me it's a base. Okay, so I can tell right away if you say, oh, if a solution has a pH of 8.6, is it an acid or base? I can tell you right away it's base. Okay, all right, what is the pH? Here we got the KOH concentration, and we want pH, okay? This is a base. So we can do a couple different things. We can find the H3O or the H plus concentration by taking, remember they both equal 1 times 10 to the negative 14th. So if I divide, I get 2.7 times 2.78, sorry, times 10 to the 13th is the H. And then I do like I did up here, take the log. Okay. Or the other thing I could do is I can take this, find the log of it, and then take 14 minus that number. Either or, you're going to get the same answer. Oh, I guess I did put that in there. Find the POH of the log of 3.6 times 10 to the 12th, again. And so you have two options, okay, when you're doing these. You can use the H3O concentration, or you can use, remember, pH plus POH equal 14. So if you know one, you can always find the other one, okay? Either you're going to get the same answer, whatever works best for you. But remember, the H or the H3O and the OH together, those two concentrations, when you multiply them, always equal 1 times 10 to the negative 14th. And the POH and the pH, when you add them together, always equal 14. So if you know one, you can subtract from 14 to get the other. Okay? So again, I showed you a couple different ways. These are just a review of the problems we already did. All right, so how do we measure pH? Well, there's a couple different things. One of the things that we do in the lab, which we don't, and if you've noticed, if you did your simulation, it was all about using pH. Okay, so hopefully you got a better idea, understanding. But we have pH meters. Ours are CBLs from Veneer. You just put the probe in there and it tells you. Okay, so one way to measure pH is a pH meter. Okay, if you want to find the POH, again, you'd have to subtract because the meters usually pretty much just read pH, not POH, okay? They're pretty accurate. They have 2 electrodes in there and they detect changes in there. Again, it's easy for us. We just stick it in there and it tells us what it is, okay? We can also use what they call indicators. Indicators change colors in certain pHs, okay? They're much less accurate, but they're very quick, okay? Really, honestly, I would use a pH meter because pH meters aren't so bad. And they used to be super, super expensive, but they're not anymore, okay? But here shows you some of the indicators. There's methyl violet, thymol blue, methyl orange, methyl red, bromothymol blue, phenolphthalein. Some of these, like phenolphthalein, just turns pink in a base. It won't tell you if it's a strong base or a weak base. It'll just say it's a base. Some of them, like here, this is bromothymol blue. It's green when it's neutral. It's yellow in an acid and it's blue in a base. So at least it gives you the whole thing. See, if it was neutral, we would know because a phenolphthalein is clear in an acid or neutral. So you don't know. And it's lightly pink and dark pink. But again, it's just a base. And then here's methyl red, does kind of the same thing. But here it changes orange in 6 pH or 5, excuse me, pH 5, and then it gets brighter here, but it's yellow here. So there's a range of them. But the big thing about these guys is they don't tell you if it's a strong acid or a strong base. Sometimes it just tells you one or the other. There are some universal indicators that change colors in 1, 2, 3, 4, 5. Okay. But again, your best bet really, you guys, is a pH meter. Okay. So there are 7 strong acids. Okay. If you ran off that sheet that I gave you or have that, HCl, you know, is hydrochloric acid. HBr is hydrobromic acid. HI is hydroiodic acid. And then we get into the oxyl acids, the ones that have oxygen. We have nitric acid. If you ever have to use nitric acid, you guys wear gloves because it will turn your fingernails brown. And yes, I'm speaking from experience. So yeah, you don't want to mess with that stuff. H2SO4 is sulfuric acid. That's battery acid. If those of you guys that have ever worked, you know, move a battery from your car and you got little holes in your shirt, that's sulfuric. HCl is chloric acid and perchloric acid. Okay, so those are the 7 strong acids. They are by definition strong electrolytes. So they're not, you know, they don't like put them on people's skin to see which ones burns better to determine if they're a strong acid or a strong base. What they do is when you put them in water, they completely break down into their positive and negative ions. That's what determines if they're a strong acid or not. If they're strong electrolytes, do they totally, when you put them in an aqueous solution, when you dissolve them in water, do they become ions? Okay, the more they do that, the stronger they are. Okay, so yeah, and again, if you remember when we did conjugate acids and conjugate bases, here's my acid plus water. So this would be my acid, this would be my base. Okay, what happens is they totally break down into whatever their ions are. Okay, they produce that hydronium, which makes it an acid, and then you've got the ions right here, whatever it is. If it was HCl, this would be Cl, you know. But again, the more they produce these ions, the stronger they're considered as an acid. Strong bases do the same thing. Okay, they're soluble hydroxides, and usually a strong base will come from an alkali metal, that first column, or the second. The alkali earth metals, they're pretty good too. Okay, the problem with the alkali earth metals is they don't dissolve in water very well. So they will become a strong if they dissolve, but your strongest bases are like sodium hydroxide. That's probably the strongest. Another name for sodium hydroxide is Li. Lithium hydroxide, you know, just that first column. Okay, those are your best ones. But again, the reason why they're considered strong bases is because they completely ionize when you add them to an aqueous solution. When you add them to water, they produce, you know, ions. They break down completely. Oh, this is supposed to be an amp. Sorry, you guys, I got moved over. I apologize for that. Okay, so it's really, you know, with these guys. And here's an alkali metal because calcium is +2, so you're going to have 2 hydroxides, but they're going to break down as well. The problem again with these guys is they're just not as soluble in water. So they don't do this as well because they just don't dissolve. But if you're talking about the first column of your alkali metals, they're the best as far as bases. Okay, there's weak acids now. What happens with a weak acid is they don't completely ionize it, don't completely dissociate and break down. And I don't know if you can see, you probably can here. Okay, we have chlorous acid, hydrofluoric acid, nitrous acid. Yeah, I can't even read it. Okay, these guys, one of the ones we use the most is probably acetic acid. Okay, that's like vinegar. Okay, what happens when you add water to them? Yeah, they do break down in ions, but not completely. So the more they break down into ions, the more they disassociate, they call it, the stronger they are considered either acid or base. Okay, all right, so there's an equilibrium. Again, you know how we did that last chapter, bringing it back again. Okay, so there's an equilibrium constant related to the acid dissociation constant. And what it is, the case of A is the hydronium ion plus the other ion that's involved, your other in your acid, are going to be the concentration of where you started. So these two together, divided by the concentration of your acid, is going to be your, like your equilibrium constant. They call it a case of A. It's the constant for acid, and it's actually a number. If you look on here, here we have them. And I will have a chart for you that has these numbers. Okay, they've already been determined. Okay, the larger the value of case of A, the stronger the acid. Okay, and again, I'll have a chart of that so you can see them. Okay, so comparing strong with weak acids, what is present in a solution of a strong acid versus a weak acid? The strong acid's going to have all those ions. Okay, they completely disassociate. So here we have, you can see whatever the A is, whatever the other ion is. Like if it's hydrochloric acid, these would be the chloron ions. If it's hydrofluoric acid, it would be the fluoric, you know. So we get water and whatever that is. When it completely breaks down. Here, a weak acid, they didn't always break down. Okay, they can't, some of them hung together. Okay, so the more they do this, the more they break down into their ions, the stronger the acid. So it's not if they eat through your skin. Okay, sorry about that. I know some of you guys really want to test that out, but we'll have to pass. Okay, so again, strong acids completely disassociated, weak acids, not so much. Okay, and how do you calculate K sub A, the constant for the acid? Okay, here we have the pH of 0.1 from formic acid. Formic acid is a very common weak acid. Okay, here's its formula. H, again, H first and then COOH. At 25 degrees, they always throw that in there, is 2.38. Okay, calculate the K sub A for formic acid. Again, it's the concentration of this versus the concentration of this. You know, we're going to take away one of the hydrogens, and then we've got the concentration of the acid when you started. Okay, we know we can calculate K sub A. We need to equilibrium the concentration of all three of these. If we want to do this, we have to get all three of them. So what we're going to do is we're going to find the H3O, and it's going to be the same. These two are going to equal each other from the pH. So here we have the concentration for the pH. Okay. All right. So what we can do is we know that the H3O equals, these two equal each other. Okay. So we take 10 times this number right here. Okay. 2.38 I got right here. This is the pH. Okay. And again, if you want to find this in a number, all you have to do is take negative 2.38 second log and you'll get this number. Okay, so now we got the concentration of both of these guys. We can plug 4.2 times 10 to the negative. It's negative third. I'm sorry you can't see that, you guys. I butted in here. So those two would go there. Sorry, this has to go on the other screen. Okay, we can set up a rice table. I know you guys love rice tables, right? So initially, it says back on here, it says the 0.1 molar solution of formic acid. Okay, so we know we started with 0.1 molar, and these are what we're producing, so they're both 0. If you remember those from our rice tables. I know that was a chapter ago. Okay, with a change we just calculated from the pH. And again, all you have to do is take the pH, which was 2.38 negative second log, and you get 4.2 times 10 to the negative third. That's where that came from. So again, they gave you the pH in the question before. Just take the second log of that number, but again, make it negative. Okay, so this is the change. And remember, minus for the reactant, plus for the product. So these are what they are at equilibrium because they started out at 0. Subtract that, and that's what you get. So then go back and plug the numbers in. So, oops, sorry. So again, rice table. We know that these two, we plug them in. This is what it was from our rice table, and this is what our K sub A would be. 1.8 times 10 to the 4th. And again, we got this number from taking the pH that they gave us. We took the second log of that, and we got this number. And that's how I plugged it in here. Okay, that's the change. And we know this was the concentration because it told us in the problem. So we go this 0, 0. So this is just like the equilibrium tables we did last chapter. And this says negative 3 and this says negative 3 if you can't see it. I'm sorry, you guys, that happened. But then you just subtract and add and you get your numbers. So then you can plug them back in. And again, remember when we did equilibrium from rice tables, we put the two products, we put products on top and reactants on the bottom. And if these would have had a number in front of them, you know, like 2 KCl or whatever, we would have had to raise them to that power. In this case, they were all 1, so we didn't have to worry about it. So, excuse me, this times this divided by this, and that's how we got our K sub A for formic acid. Okay. Okay, here's the steps. Oh, we're going to run out of time. You know what? I am going to quit here and I'll pick it up and we'll do some more K sub A problems. I'll probably have to do a few more pH and then we'll come back to this because I'm not ready to start giving you problems yet. So we'll quit right here because I'm running out of time.